Okay, this is the final instalment of the specimen paper for Unit 2 for AS Chemistry. It's question 14, 15 and 16. So, question 14, the diagram shows a Maxwell-Boltzmann distribution curve for a mixture of sulfur dioxide and oxygen at temperature T. You can see on the graph the number of molecules with a given energy, the energy along the x-axis, and then activation energy is marked. So it says on the diagram, sketch the distribution curve for the same mixture at a higher temperature. So it's this curve here, which you get 1 mark for having it moved to the right, the hump moved to the right, and 1 mark for being lower. And then it says use these distribution curves to explain why the reaction between sulfur dioxide and oxygen is faster at the higher temperature. So you'll see I've shaded in the area under the graph, and that's just to show that the number of molecules with energy greater than the activation energy increases. Then it says use the distribution curve to explain the role of catalyst and why the reaction between sulfur dioxide and oxygen is faster in the presence of a catalyst. So the first mark is for saying that the catalyst gives an alternative route with a lower activation energy. 1 mark for both those phrases, 1 mark each for both those phrases. Then where more molecules have energy greater than the activation energy is your 3rd mark. So the number of successful collisions increases is your 4th mark. Question 15. Halogenoalkanes are a useful class of organic compounds as they can undergo a number of important reactions. So bromoethane can be produced by the electrophilic addition reaction between ethane and hydrogen bromide. Explain why hydrogen bromide can be considered as an electrophile. So I've just drawn it here, and I've written the delta plus and delta minus at each end of the molecule. And the marks are coming from saying that hydrogen has a delta plus charge, and then that this is attracted to high electron density, and that would be in the double bond. Then draw a flow scheme to show the mechanism for the reaction between ethane and hydrogen bromide. So the important thing here is getting the arrows going in the right direction. So you'll see in the first step, the arrow is from the double bond to the space between it and the hydrogen. The hydrogen is shown as delta positive and the bromine is shown as delta negative. And then the electrons from the bond to the hydrogen, from the hydrogen to bromine, are moving to bromine. This leaves us with a carbocation intermediate, and you see here I have the plus charge on this carbon, and then the hydrogen has added to the other carbon. We have then the bromine with the pair of electrons from the bond, and those electrons are moving to the space between the bromine and the carbon. And then finally we have the new compound, the bromoethane, with the hydrogen on 1 carbon and the bromine on the other. So when the reaction is repeated with 3-methylpentaene, a mixture of 2 halogenoalkane products is obtained, and it tells you that this 3-methylpentaene exists as geometric isomers. So draw and label the E and Z isomers of the alkene. So I'm just going to go back up here where I've drawn it out, sort of longhand if you like first. So it's a pentaene, so you see I have 1, 2, 3, 4, 5 carbons. And then the 2 enes, so the double bond is here between those 2 carbons. And it's 3-methyl, so that's the only other group on it. So what you need to do then is draw it so that the carbon-carbon double bond is in the middle of the molecule, and just draw whatever else is on each carbon as just separate groups. So on the left-hand side here, this CH3 is this methyl group here, and then the hydrogen is just attached to this carbon here. You see it there. Then we have a methyl group, which is here, and then the C2H5, which is here. So the first orientation I've drawn, I've got the C2H5 at the bottom, and the methyl group is at the top. So they're opposite each other, so that means it is E. And then in the other one, the methyl group is still at the top. I've kept the left-hand side exactly the same on both molecules, and the ethyl group is at the top instead. So you see they're both on the same side, so that is Z. And E is German for, well, it's the word entgegen, excuse me, which means opposite, and Z is zusammen, which means the same. Then draw the structures of the two products obtained when hydrogen bromide reacts with this and indicate the major and minor products. So if we look back again at this little molecule that I drew a few minutes ago, you'll see that there are two places either side of the double bond where the where things could end up. So when we draw out the products, we see that in one of them we have the methyl group and the bromine attached to the same carbon, and in the other the methyl group and the bromine are on adjacent carbons. So this is the major product and this is the minor product, because if we look at this, there are 3 carbons joined to that carbon with the bromine on it, so that is a tertiary carbocation, and in this case there are 2 carbons attached to the one with the bromine on it, so that makes it secondary. Then it says explain why the 2 halogenoalkane products in 2 are not obtained in equimolar amounts. So you have to mention that the carbocation intermediates are produced, then talk about the tertiary being more stable than the secondary, and then the tertiary one leads to the formation of the major product. Part C, the halogenoalkane 2-bromobutane reacts with aqueous sodium hydroxide to form butan-2-ol. And then write an equation for the reaction between 2-bromobutane and sodium hydroxide. So there's our bromobutane. So you're just making sure that you have bromine in place of one of the hydrogens reacting with sodium hydroxide, and that's going to give us the alcohol. It's just substitution, and hydrogen bromide is the other product. Then it says classify butan-2-ol as primary, secondary or tertiary, explaining your reasoning. So again, I like to draw it out, and you see here the carbon with the bromine attached is attached to 2 other carbons, which means that it is secondary. So, and then that's just what I've said for my explanation. The carbon bonded to the hydroxyl group is bonded to 2 other carbons. D, when 2-bromobutane reacts with ethanolic sodium hydroxide, 2 alkane products are formed, one of which is but-1-ene. So write an equation for this reaction. So again, C4H9Br and NaOH. This time we're getting C4H8, NaBr and H2O. Then it says what's meant by the term ethanolic. Well, you could probably guess that even if you didn't know. It means that it takes place in ethanol as opposed to aqueous, which takes place in water. Then state the type of reaction between 2-bromobutane and ethanolic sodium hydroxide. It's elimination, because you're getting rid of a molecule. Then name the other product, the other alkene that's produced in this reaction. So if you can produce, you're just adding, you're taking away this this bromine here, and that means that that bond can go in one of 2 directions. I've told you here that it's but-1-ene, and that means the other product would have to be but-2-ene, because the bond is, the bromine is attached to the second carbon, so it has the double bond either has to go to carbon 1 or carbon 3, and if it goes to 3 it's between 2 and 3, so that's but-2-ene. Okay. Number 16, the second stage in the production of nitric acid involves the reaction of nitrogen monoxide with oxygen to form nitrogen dioxide. So when nitrogen monoxide and oxygen are mixed under suitable conditions, a dynamic equilibrium is established. So we look at the equation here, 2NO and O2 gives you 2NO2, and the enthalpy change is minus 116 kilojoules per mole. First off, what's meant by the term dynamic equilibrium? Well, the rate of the forward reaction is equal to the rate of the reverse reaction. That's equilibrium. And then the dynamic part is that the amount of any given reactant or product remains constant. Next, state and explain how increasing the pressure will affect the equilibrium yield of nitrogen dioxide. So if we look here in the equation, we have 2 moles of the NO, we have only 1 of oxygen, and we have 2 moles here, so we have 3 on the left hand side and 2 on the right hand side. So what you need to say in your explanation is that it's going to well, first it'll shift equilibrium to the right, which will increase the yield. So that's your state for 1 mark. And then explain why 3 moles on the left, 2 moles on the right. 1 mark for that. So equilibrium will shift to the right to oppose the change. And that's the nice phrase you want for these equilibrium questions. Then state and explain how increasing the temperature will affect the equilibrium yield. So up at the top here, you can see that the enthalpy change is minus 116. So that means that the forward reaction is exothermic, which means that the yield will decrease because the equilibrium will shift to the left to oppose the change. The reaction going that way would be endothermic, so it's going to take in the heat. And state and explain the effect a catalyst has on the equilibrium yield. Well, a catalyst has no effect at all on yield. And the reason is because it increases the forward and reverse reactions equally. And E then, the position of equilibrium is found to lie to the right, resulting in a high yield of nitrogen dioxide. Write an expression for the equilibrium constant Kc, including the units. So Kc is the concentration of the products, in this case NO2 to the power of the molar amount of products in the equation, which is 2. In the equation it is 2NO2. And then the bottom line, it's the reactants. So oxygen has no power, and the nitrogen, the NO, is squared because it's 2 moles in the balanced equation. For the units, I just do the concentration sign, concentration squared over concentration times concentration squared. We can cancel out the squared ones top and bottom, which gives us 1 over concentration, and writing that as units, it's mole to the minus 1 dm cubed. And it says, what does the position of equilibrium indicate about the magnitude of the equilibrium constant? Well, it tells you at the top here that it's found to lie to the right, and that means that Kc is greater than 1. So if you're not sure about that, go back to your notes and just look at the values. But when Kc is greater than 1, it lies to the right. And finally, nitrogen dioxide is also produced when magnesium nitrate undergoes thermal decomposition. Calculate the atom economy of the above reaction. So you can see here I've circled the NO because it's what we're interested in. And I'm going to work out the mass of the NO and then the total mass as well of everything here. So we've got 14 plus 2 16s is 32, which is 46 for the NO2. O2 is 32 with 2 16s, and then MgO 24 for magnesium and 16 for the oxygen is 40. So we have 46 for the product that we want, divided by the total, which is your 2 times 40, and it's 2 because there are 2 moles of magnesium oxide here, plus 32 for the O2, which is, oh, I'm sorry, we have 4 lots of 46 because it's 4 NO2s. So that's 184 divided by 296, and we do times 100 because atom economy is a percentage, and it's 62.2%. Okay, that is the end of the specimen paper. So I hope you have found it useful, and I just want to say, if you're watching this right before you do your AS chemistry exam, unit 2, very good luck, and just remember, try and give as much detail as you can in the answers. If you get something weird for like an organic compound, you can guarantee nobody else has ever seen it before either. Just keep your head and try and label it and, name it as best you can. Think of the compounds you do already know and see what you can apply to them. Good luck, folks.